In priority scheduling, a priority is associated with each process and the processor is given to the process with the highest priority. Equal priority processes are scheduled with first come, first served method. Even on a PC with a single owner, there may be multiple processes with different priorities. For example, a daemon process sending electronic mail in the background should have a lower priority than a process displaying a video film on the screen in real time. Shortest process first is a special case of priority scheduling algorithm where priority for process I may be calculated as 1 over next processor burst time of process I, or priority may be calculated as K, a constant, minus next processor burst time of process I. Therefore, for a process having shorter next CPU burst will have a higher priority. A priority scheduling algorithm can leave some low priority processes in the ready queue indefinitely. If the system is heavily loaded, it is highly probable that there is a higher priority process to grab the processor. This is called starvation. One solution for the starvation problem might be to gradually increase the priority of processes that stay in the system for a long time. For example, following may be used as priority defining function. Priority of process I is assigned as 10. This is a constant value added in order to prevent priority value to be negative. Priority is 10 plus the current time, T now is the current time, minus TSI, this is the time process I is submitted to the system, minus TRQ, TRQI is the time process I entered to the ready queue last time, TCPUI is the next processor burst length of process I. If priority is assigned as T now minus TRQI, then this is equivalent to first come, first served. If priority is assigned as a positive constant K minus TCPUI, this is equivalent to shortest process first algorithm. However, the priority can be assigned as combinations of these two. For example, this term is multiplied by alpha and the second one is multiplied by 1 minus alpha. This is a combination of first come, first served and shortest process first. Here an example of a system having 4 priority classes is given. Assume that priority 4 is the highest priority and priority 1 is the lowest priority. Group processes into priority classes and use priority scheduling among the classes but round-robin scheduling within each class. We have a queue for each priority. In this queues we have runnable processes. Scheduling algorithm is as follows. As long as there are runnable processes in priority class 4, just run each one for one quantum in round-robin fashion and never bother with lower priority classes. If priority class 4 is empty, then run class 3 processes by round-robin. If classes 4 and 3 are both empty, then run class 2 round-robin and so on. If priorities are not adjusted occasionally, lower priority classes may all starve to death. Shortest job first approach always produces the minimum average response time for batch systems. It would be nice if it could be used for interactive processes as well. Interactive processes generally follow the pattern: wait for command, execute, wait for command, execute. If execution of each command is a separable job, one can minimize overall response time by running the shortest one first. The problem is to figure out which of the current runnable process is the shortest one. One approach may be make estimates based on past behavior and then run the process with the shortest estimated running time. Suppose that estimated time per command for some process is T0. Suppose that estimated time per command for some process is T0. Suppose its next run is measured to be T1. Then one can update the estimate as A multiplied by T0 plus 1 minus A multiplied by T1. Choice of value of A decides whether the system forgets old runs quickly or remembers them for a long time. With A equal to 1 over 2, we get successive estimates of T0 the next time, T0 divided by 2 plus T1 divided by 2. Then T0 divided by 4 plus T1 divided by 4 plus T2 divided by 2. Then T0 divided by 8 plus T1 divided by 8, T2 divided by 4, and T3 divided by 2. The technique of estimating the next value in a series by taking the weighted average of the current measured value and the previous estimate is sometimes called aging. Aging is very easy to implement when A is equal to 1 over 2. All that is needed is to add the new value to the current estimate and divide the sum by 2. That is by shifting it right 1 bit. The algorithm called guarantees scheduling makes real promises to users about performance. One promise is if end users are logged in while you are working, you will receive about 1 over n of the CPU power. Similarly, on a single user system with n processes running, all things being equal, each one should get 1 over n of the CPU cycles. Guaranteed scheduler keeps track of how much CPU each process has had since its creation, computes the ratio actual CPU time consumed divided by CPU time entitled for each process, runs the processes with the lowest ratio until its ratio has moved above that of its closest competitor, then chooses that one to run next. Lottery scheduling can be used to give predictable results but with a much simpler implementation. The basic idea is give processes lottery tickets for various system resources, such as CPU time. Whenever a scheduling decision has to be made, a lottery ticket is chosen at random. The process holding that ticket gets the resource. When applied to CPU scheduling, the system might hold a lottery 50 times a second, with each winner getting 20 milliseconds of CPU time as a prize. More important processes can be given extra tickets to increase their odds of winning. A process holding a fraction f of the tickets will get about a fraction f of the resources in question. Fair share scheduling. So far, we have assumed that each process is scheduled on its own without regard to who its owner is. If user 1 starts up 9 processes and user 2 starts up 1 process, with round-robin or equal priorities, user 1 will get 90% of the CPU. To prevent this situation, some systems take into account which user owns a process before scheduling it. In this model, each user is allocated some fraction of CPU and the scheduler picks processes in such a way to enforce it. Consider a system with 2 users, each promised 50% of CPU. User 1 processes ABCD, user 2 process E. If round-robin scheduling is used, a possible schedule sequence is A, E, B, E, C, E, D, E, and then AE, BE, etc. If user 1 is entitled to twice as much CPU times as user 2, we might get ABE, CDE, ABE, CDE. In scheduling real-time systems, time plays an essential role. Categories of the real-time systems are hard real-time, there are absolute deadlines that must be met. Soft real-time, missing an occasional deadline is undesirable but nevertheless tolerable. In both cases, real-time behavior is achieved by dividing the program into a number of processes whose behavior is predictable and known in advance, which are generally short-lived and can run to competition in well under a second. When an external event is detected, scheduler schedules the process in such a way that all deadlines are met. A second categorization of the real-time systems is as follows: periodic, aperiodic. In the periodic case, they occur at regular intervals. For aperiodic case, they occur unpredictably. A system may have to respond to multiple periodic event streams. Handling all streams may not be possible. A scheduleable case satisfies the summation I from 1 to m Ci divided by Pi should less than 1, where n periodic events exist and event I occurs with period Pi, n periodic events exist and event I occurs with period Pi and requires Ci seconds of CPU time to handle each event. For example, consider 3 periodic events with periods 100, 200 and 500 milliseconds. So the first one appears 10 times in 1 second, the second one 5 times, and the third one 2 times in a second. If CPU time assigned are 50, 30 and 100 milliseconds, then system is schedulable. The first one uses 0.5 second, the second one 0.15 second, and the third one 0.2 second. If we add them up, it is less than 1. With an added fourth event with a period of 1 second, will remain schedulable as long as it does not need more than 150 milliseconds of CPU time per event, because the summation of all these is 0.85, so the difference between one is 0.15. So it makes 150 milliseconds. So far we assumed that all the processes in the system belong to different users and are competing for the CPU. But one process may have many children running under its control and may have an idea of which of the children are the most important or time critical. None of the schedulers discussed so far accept any input from user processes about scheduling decisions and hence not optimal. The solution is to separate the scheduling mechanism from the scheduling policy, which means the scheduling algorithm is parameterized in some way and the parameters can be filled by the user processes. Thread scheduling. When several processes each have multiple threads, 2 levels of parallelism are present: processes and threads. Scheduling in such systems differs substantially depending on whether user-level threads or kernel-level threads or both are supported. Consider user-level threads first, in which kernel is not aware of threads, picks a process given its control for the quantum of the duration. Then, thread scheduler inside process decides which thread to run. No clock interrupts to multi-program threads, hence a thread may continue running as long as it wants to. In case that processes threads have relatively little work to do per CPU burst, each thread runs for a little while, then yields the CPU back to the thread scheduler. In a system supporting user-level threads, suppose that we have process A and process B. Process A has 3 threads and process B has 4. The operating system kernel picks a process for execution. Suppose that A is chosen. Then the runtime system picks a thread within the process. Suppose that the order in which threads run is as given here. In this figure, possible scheduling of user-level threads with 50 millisecond process quantum and threads that run 5 milliseconds per CPU burst. It is possible to have A1, A2, A3. This is scheduled by the process A scheduler. And then because the time quantum is not expired, again A1, A2, A3. This is repeated until the time quantum for process A expires. Notice that because time quantum is not expiring, it is not possible to organize the scheduling of the threads as follows: A1, then process B, B1, then comes A2, B2, etc. However, if we have kernel level scheduling of the threads, in that case, kernel picks a thread from the processes, and then it is possible to have A1, A2, A3, A1, A2, A3, or A1, B1, A2, B2, A3, B3, etc.